Hi, good morning. Can you hear us?
Yes, we can hear you.
Okay, great. Yeah, so welcome. So this is a webinar on this where we are at the moment with the CIRCOMOD project. And to some degree, it's more or less an open project meeting session. In this next 1.5 hour, we will go through where we are in the project, present our current results, and we're happy to share them with the rest of the world, the online participants to this, and to also hear your feedback. We are now 3.5 years into the project. We're starting to work towards finalization. And again, for us, this open part of our project meeting is an interesting way to also make sure that we get feedback on our results. So maybe you move to the next slide and you can skip the first one because that's just my name. You have to click on the presentation, I think, and then you could probably move. You can see the slide also online. Can you confirm?
Yes.
Okay, great. Yeah. So the CIRCOMOD project is about the use of materials and the interaction of strategies to improve the efficiency of material use with climate policy. And we started off in a project proposal with this graph where we depicted that in principle we have materials that can be used and they're extracted and potentially become waste in a linear system. And as in producing these materials, we use energy, but they also provide all kinds of services to the economy. And yeah, the fact that they are related also to energy for their production, that means that they also related to the climate problem. And on the right, you see a graph which indicates our expectations where current policies go and where we need to go in order to meet the 1.5 degree target. And so this graph is actually from about 1 or 2 years ago, where we make estimates of current policies. Over the last few years, current policies have not improved a lot. If anything, we probably last year went a little bit backwards globally with the US stepping out of the Paris Agreement, which means that current policies clearly are not in line with what is needed for the 1.5 degree target. In Europe, at least, emissions are going down and are closer to a trajectory which could be Paris aligned. But still the question, if we want to reduce emissions, can we potentially also do that by reducing materials, is a very important one, because it could potentially provide an additional route to move downwards from current policies to 1.5 degrees. And that is what CIRCOMOD is really about, trying to see whether circular economy strategies could contribute to meeting climate goals, and if so, to what degree. Can you click? Yeah, so that we're interested in that blue arrow. Because traditionally in integrated assessment models, we do look into, can you make steel as a material more efficiently? We do look into, can you use other fuels to make steel? But traditionally, we did not really look into, do you need so much steel to start with in the first place? Yeah. Click again, please. Yeah, so that means that we have to start relating that material use to different parts of the economy as a whole. First of all, the energy system, but also to how it relates to the economy and what kind of strategies we have in reducing material use, like repairing, recycling, and manufacturing things in a different way. Click again, please. So the objective of the CIRCOMOD project is to model the circular economy strategies and how they impact greenhouse gas emissions and resource efficiency across a wide range of material sectors, individual EU countries, and the global scale. And yeah, we divided that into all kinds of sub-questions, all kinds of work packages. And so in the next presentations, you will actually see these work packages being represented. including work that we did on the efficiency in different sectors, both on demand and supply side, and developing new scenarios. And this is the setup of the CIRCOMOD project. You can click again. In what we also did in creating the CIRCOMOD project was bringing together both experts on material use, but also different types of modeling groups. And we thought it would be interesting to at least have 3 modeling groups represented in the project. That's first of all more macroeconomic models, which could provide us much more insight on the relationship between material use and all kinds of services these materials provide to the economy as a whole, and therefore also the potential macroeconomic impacts of CE strategies. The second set of models, please go back, is the integrated assessment models, and they can provide insights mostly into what does it mean if we reduce material use for greenhouse gas emissions, because they also represent the energy system. And finally, we wanted to have the material flow and industrial ecology models, which have much more experience in representing material cycles. And that also means that we can provide insights from these 3 types of modeling groups and share them. And so, for instance, the way that stock dynamics work might be information that we can share from the material models to the macroeconomic models and integrated assessment models to represent stock flow behavior better. Yep. Yeah, now we are now 3.5 years into the project. And what we have done so far is that we reviewed different models and policies. We worked on an analytical framework. We reviewed all kinds of supply and demand reduction options. We set up a data infrastructure and we started data collection. We worked on model improvements, and we have started to do a first exercise on scenarios. And it also means that the last half year of the project is mostly focused on developing those scenarios further, and so that we can provide a potential answer to the question, how much can circular economy indeed contribute to mitigation? And so also in what we present today, you will see that this first start of the working on scenarios will play quite a central role in the presentations. And so when we started to think of what could be a well thought up design of scenarios within CIRCOMOD, we thought that maybe something like this might be the best way to look at it. So first of all, look at the vertical axis. And so normally if we would look into how to move to Paris Agreement, we would look into the effect of climate policy. We might start from a world that is implementing current policies, which was this horizontal line in the graph that I showed before. And then we run a scenario where we do something that is consistent with the Paris Agreement and look into what is needed to move from the one scenario to the other. What would be needed in terms of additional renewable energy or energy efficiency, but also what would be the cost of that. So this is one, we thought, an important dimension in our analysis. The second important dimension in our analysis is, do we have a circular economy strategy? And so we could run without circular economy strategies or with circular economy strategies. And then we get this matrix that is shown here, which first of all, on the left top corner has no climate policies and no circular economy strategies. Then if you look at the left bottom, it has this traditional analysis of climate policy without circular economy. And then you can compare it with the right bottom situation where you have included circular economy, and you can see what the impact is of that. So it's a logical structure that can help us to answer the question that we were about. Can you go to the next graph? So one activity we did as well in CIRCOMOD was reviewing the literature. And we started with this R strategies from refuse, rethink, reduce, and looked into what the literature says in different sectors on whether how much these strategies have been analyzed. Yeah, in looking at those 9 possible R strategies, we realized that there is some overlap between them. And also it's a little bit too much for us to put into a scenario framework. And so we grouped them a little bit into 3 major categories of R strategies. One set, and you can click again, that is much more about smarter product use and manufacturing. So making sure that you use less material for the same amount of surfaces. The second would be much more related to slowing down the material use in society. And so, for instance, extending the lifetime of use. And then finally, the third set of options would be much more related to closing this, the use of materials. So after they're used, bring them back and recycle them. And so we, instead of looking at 9 different strategies, we decided to look at 3 major focus areas: narrowing, slowing, and focus. Closing, sorry. Can you go to next? And that we could bring into that scheme that I already presented. And so basically we had that 2x2 matrix of climate policy, and then on the other axis, the CE strategy, no or a lot. But then we can also introduce them into these 3 steps. And so first analyzing what would be the impact of narrowing strategies, then separately looking into slowing strategies, looking into closing strategies, and then adding them all up, which also allows us to get a little bit more deeper insight in what is the effect of different strategies. On the climate axis, can you go back for a second? I will say click when you. On the climate axis, we did so far analyze strategies consistent with well below 2 and 1.5. It might be that we actually decide later in the project to focus mostly, as first of all, in strategies to stay well below 2, and then see what the additional impact would be of a circular economy strategy. Yeah, please go to the next slide. And I've just added this slide to show you that we are already doing such analysis. And so you see here the different CE strategies from left to right. First, the no CE strategies, the narrow, slow, close, and then the combination of them all. And then we analyze with different models what that impact is on both material use and finally also emissions. In this case, we're showing the material use in the transport sector, but we can do that for different strategies. I'm not going into details because that will be done in the next presentations. Can please? Yeah, and then we can also analyze in a similar way how this impacts greenhouse gas emissions. Again, we're using different models and looking at these different strategies of narrow, slow, and close. Yep, you can. And so this is a quick introduction of where we are now with the CIRCOMOD project and what the basic intention of that project is. I promised that this was actually the most boring presentation, because from now on we go into much more detail on the different presentations, and we start with Peter looking into the building modeling.
Okay, now I need to raise the pressure to increase the activity. So yeah, Peter Berrill from Leiden University here. And I will be introducing some of our recent advances in our circular economy modeling for the building sector and what that means for material demands and later greenhouse gas emissions. So a brief reminder of why we care about buildings. It's the largest anthropogenic material stock in use today. comparable with infrastructure, but yeah, a little over than half of all anthropogenic material uses in stocks are in building sector. And in the next slide, we see also a similar pattern for material flows. So this is work also part of the material from the CIRCOMOD project led by Martijn van Engelenberg, who has taken the stocks and used assumptions about lifetimes to estimate preliminary material flows for each for detailed sectors. This will be refined with our simulation results, but we see that a lot of the buildings account for a large share of annual material flows. So this is a overview of how we do our modeling of the stock flow service nexus in CIRCOMOD. So we have a bunch of different data inputs, scenarios defined by the SSPs and their population, GDP, and so on. These feed into the integrated assessment and material flow models. And they basically define the product stock, the material stocks, and the material inflows and outflows in the scenario projections. Next slide. A reminder of what's included in these circular economy strategies for the building sector. So we, as Detlef introduced, we group circular economy strategies into the narrow, slow, close families. And in buildings, that means lowering floor space reduction. Something a little bit different that we did in this project about the floor space reduction is to make it dependent on the population projection expectations and also the starting levels of floor space. Narrow also includes increase of wood-based construction and lightweighting, where similar product service is delivered with less material requirements. Then slow refers to lifetime extension, but also increased material reuse. And close is about improved or increased material recycling. So the questions for buildings specifically is what is the contribution of these different families of strategies to reducing material demand and greenhouse gas mitigation? And also, because we present a global analysis here for 13 different world regions, we can see that some strategies are more and less effective in different regions, and then we can try to understand why that might be the case. And also how are the different potentials influenced by demographic factors or the starting stocks. Here are global product stocks, so total floor area in the 13 CIRCOMOD regions and global total for a set of different scenarios, including narrow, so close, but we just see differences in the total stock here. So the only difference we see is between the baseline and the narrow, so the reducing demand. There's a lot of differences to unpack between the different regions. First of all, we can see that in more developed regions, we actually have some declines in the absolute levels of stock. That might happen in a baseline case anyway. Most obvious example is Japan, but also China. Some of Central Europe starts to decline the total stock at some point mid-century or so. Narrow can bring that decline sooner and also to a lower level. A lot of the growth is expected in developing and population growing regions. That's predominantly South Asia, India, Sub-Saharan Africa. Yeah, I think we can move to the next slide. Here we show the difference or the effect of each strategy or of narrow and slow. So it's the baseline SSP2 minus the implementation of narrow and slow. And we can see here where these strategies are, how large they are by different regions. in the beginning, narrow has a large effect in everywhere, but also including developed regions like the US. And after 2060 and so on, then the effect is much larger in developing regions, sub-Saharan Africa and India, South Asia. Narrow also has a earlier effect, so it's basically working almost immediately. Slow, by the end of the century, it has a similar magnitude as narrow, but it takes a lot more time to kind of ramp up. And regionally, the impact of slow is seen a lot larger in China than in other world regions, whereas narrow is initially everywhere and then later mostly in the developing regions. Yeah, we can go in the next slide. Here we show differences in total material inflows for steel in buildings, and also comparing the three scenarios or the three strategies. Narrow can already reduce material demand by 30% by 2030, whereas slow can reach that effect by the end of the century. And the future material demands dominated by China, India, other Asia, and sub-Saharan Africa. There's also a large complementarity here. So when we add narrow and slow together, there's a big additionality. Close is not represented here because we show total material demand, but if we go to the next slide, we can also see impacts on virgin steel requirements. What is quite interesting when we look at virgin steel is that in a couple of, let's say, stock-rich regions, Europe, US, and so on, by 2050 or so, we actually already don't need any more primary or virgin material input. And we can dig into the model a bit to understand this better, but it is about the relative size of existing stocks and outflows compared to what is needed for future stock growth. So it's quite notable that even without narrow or any other circular economy strategies, that in certain developed regions, that the virgin material demands already are getting quite low. Obviously, narrow accelerates this reduction in primary material inputs, but it has a larger effect in, let's say, developing regions. With combining all of these three strategies together, we can reduce the peak by about 2/3 or by about 1/3 of the total material demand, and it also shifts the total demand about 10 years earlier. By the end of the century, the combination of these strategies can reduce total primary material inputs by over 2/3. We can also look how the different potentials vary by the starting stock. So by design, we set up the assumptions about narrow, that the places that start with the larger beginning stock have a lot more space to reduce. So we can see for steel and for concrete that basically the larger the beginning meter square per person or starting service stock, then the larger the reduction is over time. In here we see 2060 in concrete and steel demand. For virgin steel, there's a similar demand for slow, so that the places that are stock rich, that have large meter square per person, also tend to be places with slower turnovers, with longer lifetimes. So there's also a relation that slow is more effective in places that are quite stock rich to begin with. For close, we don't really see this relation. And then a summary of total effects by the material categories. In terms of overall mass, they're dominated by concrete and brick. We need to check about cement. Maybe there's if this is double counting or if this is separately accounted from concrete. And we will have similar effects we will expect similar effects on greenhouse gas emissions. We will show them soon how they affect each material group. And just to sum up, we can, with the combined circular economy measures, we reduce total material demands by around 40% by 2060, or 65% by end of century. In the near term, construction demand is dominated by China, also US, but from the mid-century onwards, the construction inflows and material inflows are much more dominated by growing regions. In the long run, narrow and slow have similar potential, but narrow works a lot sooner and is more effective in these growing regions, but also, interestingly, in the US, where there's high stock to begin with. Some things we can take for discussion and interpretation of the results. There is still quite an inequity in meters squared per person, even in our baseline scenario especially in our baseline scenario about how different regions grow or maintain their stocks. So it's I think that's important to consider how long we can expect the existing inequities in service consumption to continue, especially we see in the large effect of narrow in the second half of the century. That's about a widening gap in baseline versus narrow service meter square per person in the developing regions, multiplied by a very large and growing population. So it's the global effect of narrow is very sensitive to what we assume the floor space growth to be in developing regions. In mature regions, for some virgin materials, for example, virgin steel, we already reach very low material input by mid-century before applying circular economy. So that also reduces the impact on emissions of applying circular economy in places where we anyway expect there to be lower primary material demand. And yeah, I think what's quite nice about the analysis here is that we bring a lot of different dynamics together. We can make kind of guesses about the individual effect of all these strategies, but there are many different factors which influence the total results. It's about the starting levels, the population growth, the lifetimes, and the total potential of each of these strategies cannot be understood until we model it together. And I think what's important to see here is that there is, at least for narrow and slow, quite a large complementarity, so that it makes a difference to do these together. That's all for me, and welcoming the discussion and questions afterwards. Thank you. I guess we do the Q&A at the end, or? I think so, yeah.
No, sorry, just a clarification question on the narrow mix, because for instance, in our case, we simulated, I mean, the major effect from the narrow mix of policies come from the modal shift of transportation. So I just want to know if you have this type of.
I was presenting the buildings results here, but the question is about transportation.
Mm-hmm. Now, which type of narrow policies are you studying? Because in our case, the major effect that coincides with what you showed. By the way, I'm surprised that we are very much aligned with your result with the CG model.
Yeah.
Is that the main advantage come from the fact that there is one narrowing policy is the modal shift, so moving from cars to trains or okay. So I was wondering if you have the same results or the same motivation for the result that you are observing.
So what's meant by narrow here, or what narrow covers, is demand reduction and increased wood construction and lightweighting. But I presume
Okay.
I presume that the majority of the reduction is coming from floor space reduction, and it's not explicitly clarified, but some of this floor space reduction can also be from a mode shift in the buildings from single family towards multifamily. This is only buildings here. Yeah. Okay. Yeah.
All right, so thank you very much, everyone. My name is Meng Jiang from Norwegian University of Science and Technology, working with Professor Edgar Hirtwesch. And yeah, this is campus in the Norway now, but it's a little bit snowy, but temperature goes up, so we do not see so many snow here. Yeah, it's so pleasant to be here to present our works to relate to the machinery and this equipment, the second most GHG intensive material use. Yeah, next slide, please. Yeah, and the first question is like why the machineries are important. And for example, we're using the resources from the nature and also get the raw materials. We produce them as consumer goods and capital things. They provide services, and in the capital production, we see machinery as a key component. If we look into the GHG emission or the metal uses, you just second to the buildings. So that is super important. Yeah, next slide, please. Yeah, so we see the machinery and the equipment drives 8% of global emissions, 32 of iron, steel emissions, and 47 of the aluminum emissions. And also it's a secondary for the resource repository, just like a lot of metals or plastics are using in the machinery equipment sectors. Yeah, next slide, please. So when study this sector is super important. Just second to the buildings, we find a big gap, a data gap. So in the literature, and also we find the industrial equipment, machineries remains the least studied area of the metal use and still poorly understand. The sector is highly fragmented and non-standardized. For example, for buildings, commercial buildings, residential buildings, they're sort of similar to vehicles. But for machinery equipment, the machinery in the manufacturing sector, for example, chemicals, vehicle making, they are totally different. So it's non-standardized. And also it's a core material base for the future technology developing in the future. For example, solar panels for all the technology supporting the renewable energy. We need the machinery. Yeah. So the first question, how can we first understand the historical evolution of machinery when the data are so limited? Most ideal way is to running a bottom-up material flow analysis, but detailed industry data are missing. So we are thinking the top-down IO offers a useful starting point. And we instead of looking into the material stocks, we're using the metal footprint, which reflects the primary metal allocated to the final demands in the capital formation. It's not the metal physically presented, but it's a proxy for that. In this cases, before going to the dynamics, we look into the production firstly. We see like the firstly, producing those machinery equipment, we have 4 gigatons carbon emission each year, GHG emissions. And the second figure shows in the right side, just like which sector are using the machinery. We see the machinery and the manufacturing services. They are using a lot of machinery for this part. So the left side is the producing, the right side is the consuming. Yeah, next slide, please. Yeah, then we're combining the philosophy from material flow analysis, dynamic one, combining with the input data. We're assuming the capital formation as a process of stock formulation to track the embodied footprints of the machinery. Then we have a dynamics through times. Next slide, please. Then we have empirical analysis. Firstly, we can see this is original machinery equipment patterns differ substantially. Looking at the metal embodied in the machinery stocks, we see rapid growth in the developing regions. For example, you can see the orange and the red parts mostly are from the developing regions, and for the blue and the pink parts are from the developed areas. So you can see an increasing of the metals embodied in the machinery stocks happens in the developing areas. Yeah, next slide, please. We're also able to capture the how much when are the stocks accumulated. Here's also the metal footprint embodied in the stock rather than the metal stock. The different colors represent the years of construction. For example, the green part shows the recent added value, added stocks. And you see, for example, in the European areas in the top and the left, the stock add in from the last decades are about like 1/3 of the total stock we are using for machinery. And for developing world, for example, China, the second in the middle, you'll see the last decades about like over half or 2/3 of the stocks, also for the other Asian countries. So you can see the different patterns of different groups of the countries. Yeah, next slide, please. Yeah. And for the Excel base, for the global analysis, where we only have like 6 sectors of the machinery. But if we're going to national statistics, national IO table, they can provide more details on that. So we're looking to the US EIO. They provide like 70% of the types of machinery stocks, machinery and equipment. So Edgar and together with me, we're looking to those parts. We're able to capture the carbon emission for the machinery and where does it come from. We see largest part for the orange parts are from the producing material. So we see the producing materials are highly relevant for all the emissions related to producing the machinery parts. Yeah. Next slide, please. We find one thing very interesting, just like there's two ways usually people modeling the capital things. One thing is the financial world. For example, we have a new car, and after 5 years, we resell the new second-hand cars. The price will be halved. But if we look into the physical world, for example, we look into retirement functions, 95 cars are still on the road. So in the financial book, we only have 50% values. But for the materials, we have 95% of the materials still in the stock. Next slide, please. Yeah, we model the two parts in the same map. We are able to see, for example, the line in the upper area, we're using surviving curves. That's actually the metal reflect the physical world. But the bottom line, you see that's line, that's by the depreciation. That's the values in the financial book. There's a huge gap between that. So financial values follow depreciation. They drop fast on paper, even when the equipment keeps working. And the physical counts show the real material still in use. They are only full when the equipment is physically tired. So that's why, for example, in Japan, we see the physical stock keep rising while financial values look flat or declining. And when we look into this, we still consider and discussing just like the first implication is like when book values fall to 0, but materials remain in the stock. So we see the gap. This gap reveals maybe the circular economy opportunities because these materials can still be create values depending on recovery and the processing costs, but in the book, the values are still 0. So probably then can be the opportunities for circular economy in this part. The next slide, please. Yeah. And also, because we've identified data as a big issue here, we're wondering what kind of information can we obtain from data set. So we moved to another research on those parts. Yeah. Next slide, please. Yeah. We're trying to compare the LCA data from different type of IOA data because the data is really fragmented. We're combining the LC database, EIO database, and national EIO database together to see the data quality and the information. The next slide, please. Yeah, firstly, we compare the IO and LCA data mostly from the eco-event. We compare the multipliers. So you can see the dots for different types of machinery and also the multipliers. The yellow dots are from eco-event. It's a high range, but mostly you can see the blue dots are from the IO table. And mostly you see the data fit in the range. So we say both data, okay, they agree with each other. But we feel one thing is a bit weird, just like eco-event data seems a bit higher. Yeah, for some regions, for example. So yeah, difference. This may be because of the differences when consider the global supply chain for the national IO table or global MRO data. But one is from the bottom up analysis, one's from top down analysis. We're not very sure just like what difference happens, but in general, they agree with each other. Yeah, next slide, please. With that, we are able to identify there where should efforts to be in to solve the data gaps. For example, you see in the left part is the total emission. For example, you see the electrical machinery from China, the vehicles or the office is a high emitting areas when we producing the machinery. And also the right side indicate the degree of differences within the sector, just like how large the disagreement or variations in the emission multipliers within the sector. We also see the electrical equipment are facing a large range of differences. So here probably will be where we should put the efforts on solving the data gaps here. Yeah, next slide, please. And what LC and IO tells about machinery is that national IO provides more details. Global IO give us the supply chain information. So maybe combining the two can be an option. And also LC equivalent offers the most detailed product level information, but the variation is a little bit higher. So we're consider what can be the representations from that and the data quality there, because the equivalent there also lack a lot of details among those. Yeah, next slide, please. Then move to our especially linked to the CIRCOMOD, because we're trying to solve some data issues. We have top-down measures. We're asking what about the future? And next slide, please. Yeah, as you know, the team is developing the Excel base. It's a global multi-regional IO tables, and also all the models containing 48 regions and 200 products. And we're trying to extending the Excel-based models into the futures. So we see the from historical part, we have the Excel base as a whole. Then we have a production module, try to change the production and also industrial sectors, as well as the efficient improvement through the framework. We have emission modules, supply chain modules reflects sort of about the trade parts, and also macroeconomic modules to determine the final demands in line with the GDP. And also the capital parts. Now we're just using the static endogenous investment modules, but we're hoping to adding the stock as we presented in the first part to have a dynamic flow and the stock to determine the capital in the parts. And then altogether we also have a what if scenario modules to measure the circular economy measures and the shock to the system. What kind of information we will have or impacts we will have when we using the circular economy measures. Then we have a full scenario output. But this is mostly about the supply chain. It's not the full-fledged model, but can tell us more about the supply chains and also the demand and the supply parts. Next slide, please. Yeah, we have some first result from that. For example, here for the GG emission, we're more stable for this part. For example, here is a global consumption-based carbon emission by expenditure categories under this SSP baseline scenario. And we are also linking that to the CIRCOMOD part. Yeah, we have like shelters, food, clothing. We see manufactured products also drive a large part of the emissions. That's more related to the material production. Yeah, next slide, please. Then we contain 12 regions in our scenario models. For example, we see a saturation in China, and the first one is Canada and Australia. We see also some declining. European, mostly the saturated part. Yeah, this is from the consumption-based perspective rather than the production perspective. But still, we can see we need a lot of efforts in the demand cutting for this part. But this is the most baseline and is our preliminary results. Yeah, next slide, please. Yeah, and also there's a lot of effort should be made in the industrial system. Here's the multipliers when we are just like trying to have for different sectors, shelter, food, for example. Yeah, to align with the SSP 1.5 scenarios, we need to have a huge declining for the carbon emission multipliers. Yeah, this shows the data from the 6 regions out of 12. Yeah, we can see, for example, there are still some maybe declining in the developing areas, but hopefully the declining of the industrial system, decarbonization of the industrial system are needed. Yeah, next slide, please. Yeah, then the GG emission parts are sort of okay because it's our new model and we're on the developing those parts. And when we move into the materials, there are some like issues try to solve, but here is our first result about metal production by regions, and mostly we can see there's an increasing and declining for metals, and also there's a little bit drop between the empirical analysis and also the scenario parts. We're trying to solve this part, but initially we're thinking because of we have a large demands for the renewable energies for the new energy system, we need a lot of machinery and also metal use to support those transitions. So here will be a key part, and also will link to a high carbon emission. Yeah, next slide, please. Yeah. And there's a line between the historical and empirical parts as we presented it firstly, and then we project those into the futures. We see the European, Japan, China, and Africa. Those are metal footprint embodied in the machinery capitals. It's also a testing result for SSP2. We see a European and Japan, we see a declining or saturated parts. While China or Africa developing areas, we still see a growing for the metal footprint embodied in the stock. Next slide, please. Yeah, and also there are some module we are developing recently. It's about like the what if scenarios, just to see the circular measures, what is the impacts added to the baselines. For example, the policy shock to the current baselines. So we're determining three perspectives. The one is asset demand, the direct, for example, the demand cutting or rebound effect, and also demand structure changes, like in the investment, how much goes to the construction, how much goes to the machinery. The second part is about the production structure. We're trying to modify the technical coefficient matrix that align with all the technology improvements or technology substitutions for those parts. The second part is about the eco-efficiency. For example, the transport changes, input substitutions have more secondary materials inputs, and also changes in environment stressors. With all this, we're able to testing the what-if scenarios in the new Excel futures model to see the impacts. Yeah, next slide, please. Yeah, a quick summary of the work we have been done for the machinery parts. Firstly, the machinery equipment is significantly affect the product life cycle impacts and shall be included in the scenario analysis. What we find the data are so poor and very limited and fragmented across all the sectors here. So yeah, the input-output models offer a basis with when the detailed data are unavailable, and we're trying to further this pathways to using the Excel futures to capture some future dynamics. Yeah, the machinery equipment are highly diverse and poorly standardized. So from top down, we need a IO, but bottom up from the LCE data are also very relevant. The IM and IE model should be flexible, combine IO-based top-down estimations with the case-specific analysis to capture the machinery capital dynamics, although the research in this area remain very limited. And we thank you that CIRCOMOD can give us support for the research on this machinery and this equipment, and we're hoping to push that further. Yeah, and next slide, please. The final one, and thank you for the attention. Thank you for the colleagues in NTU, and this is Northern Lights from the NTU campus. I think 2 years later, the ISIE, the Industrial Ecology Conference, will happen here. So you're welcome to join. Yeah, we'll see the solar night, or just like sun will never goes down. Yeah, during the summer. Yeah, thank you very much, and yeah, we'll happy to answer your questions later.
One second. So we just want to indicate that we have about 20 people online. So that's quite nice. So just we don't see it in this room, but just for notification.
Okay, great. Thank you. So I'm going to present and discuss the incorporation of circular economy options mechanics into a CG model.
Then what are the main challenges or what are the main features of doing this introduction and model development? And then we're going to present some, let's say, preliminary results, but insights and findings that we had by running the model on a few scenarios, a baseline scenario, a decarbonization scenario, together with different circular options. And I'm going to conclude with what has been the main challenges, insights, and what we can further improve. Now, why it is important for, let's say, a CG model to include the circular economy options? The CG models are supply-driven models, so they are, let's say, growth and economic implications and all the impacts are driven by how the supply can meet demand, how, let's say, the economic system actually have access to resources and generate resources in order to increase economic activity. Reducing emissions requires the adoption of technologies and fuels that might not always be available timely or might be available at expensive either capital cost or labor cost. So by introducing circular economy options, one has the ability not only, let's say, to substitute different materials with different energy intensities and different carbon intensities so as to ease the decarbonization process, but from a CG perspective, it free ups the room, so it free ups resources that can be used elsewhere in the economy. And this has, let's say, an horizontal beneficial effect through, let's say, key variables such as wages or capital costs. This is what we're going to discuss. So reducing the energy and carbon intensity of materials is an essential part of this model improvement. Another very important part is to identify the technologies on which the economy is dependent in order to make its decarbonization. And together with the technologies, the materials associated with that. Of course, depending on the granularity, I mean, although you can see we have stretched the model to increase the sectoral granularity, and this is extremely challenging from a computational perspective. You can only have few materials associated with key technologies. I mean, we have steel, copper, I mean, you will see, but we cannot go in much detail in covering all materials critical for the technologies. Dependence on materials, so who is producing the materials, who is using the materials. This is another very important element that can be captured by the CG modeling. And then from exactly the definition of these different circular measures, circular economy measures, we can identify the room and the importance of resource efficiency and productivity improvements and how this can impact economic growth. Waste and recycling sectors, which we now, after doing also the scenarios, we realize that they are even more important because these are the suppliers of the secondary, the material or let's say the resources that is necessary to engage to circular economy. So these are, let's say, elements that are quite important and can drive the results considerably from a CG economic perspective. So you can go to the next slide. So moving from a linear to a circular, let's say, representation actually involves of extending the model in a number of directions. The first direction is to introduce the primary production, the secondary production, extraction, and recycling of materials. Another direction is to introduce the stock, of, let's say, either the waste and then the scrap that is available in order to make, let's say, recycled materials and have a recycling rates. Then it is about reformulating or let's say changing, as we're going to see, the substitution possibilities for each production function for each economic activity. So how essential are some materials or some the possibility to engage from primary to substitute primary production to secondary production, how easy you can do and to which extent. So these are, let's say, the main elements that are introduced from a CG perspective in order to allow to model circular economy options, together with additional details on the investment matrix, on the consumption matrix, on the production function, and on the explicit representations on material productivity. And so how much material is used, is required in order to produce 1 unit of output. The mechanics here, so for example, the easiness to substitute primary to secondary or to the stock that is available is very hard to trace. I mean, in some given both the aggregate nature of some of the sectors, but also the complexity that you need, or from an accounting perspective, to have vintages of ages. I mean, on buildings when you replace, on cars when you replace, on equipment when you replace. So to keep the track of all this is quite, let's say, demanding from an accounting perspective. But all these are required in some respect in order to allow to have a good accounting and estimation of the circularity potential and the benefit from an economic perspective. So just let's say very quick. So the geometry model, let's say, has been extended in this direction. Reserves or resources are a separate production factors. Firms are minimizing costs. Households are maximizing a less utility function. And then we have secondary markets, and then we use, let's say, material intensities in a satellite model. I mean, we have the monetary, let's say, price and volumes in the CG model, but we have to keep the material intensity balance. You use a satellite module. So the next slide, please. So one, let's say, of the elements has been to change the production structure. So for each economic activity, to change the CS nesting to allow better substitution possibility. So for example, here you can see on the first, on the left, in order to produce, someone requires, so let's say the extraction sector needs to have reserves, and then all other production factors follow a nesting scheme. So capital, labor, and energy, then intermediate input, capital, labor, and energy, and so skilled and unskilled, and so on. But here it shows that at the first level, it's very important to have the reserves are essential. And the same for, let's say, the primary production, you need to have the raw material in order to produce. For the, let's say, final products in manufacturing, so the main, let's say, element here is the selection between primary and secondary, let's say, material in order to introduce into their production function. Now, this is, so there are, I'm not going to show all CS, let's say, functions, but this is different per economic activity. And it is, let's say, it drives this substitution possibility, drives, or it is a significant factor determining the overall adjustment of the system. So if we can go to the next slide. So this shows the number of, let's say, activities. It's 86. I mean, some are not. You can see there's a quite big detail from industry to, let's say, services, but also to materials, non-metallic minerals. I mean, I will not read one by one. A key, let's say, feature that actually will allow us to draw some conclusions once the simulations become more mature is the separate representation of race equipment manufacturers. So this EV transport equipment, advanced electric appliances, equipment for PV panels, wind turbines, batteries. So the explicit representation per country of the factors that are producing this equipment and linking this equipment with materials that are necessary and having the reserves per different countries and stocks of primary and secondary production gives a step forward in order for a better understanding, both from an economic perspective, but also from a security of supplies perspective, how the transition to a decarbonized energy system will look like. Now, before we go to the scenarios, I thought there was a slide on GEMI 3, just to say a few words. So the additional element of modeling here is that the model is recursive dynamic, so there is no intertemporal optimization on economic agents. There is, though, some reduction on capital cost through learning by doing. So the more you, let's say, you produce of a technology, the less the cost of this technology is. And then all countries are linked through bilateral trade transactions and materials are represented as discussed. So the scenarios, we are now at the phase where we have produced preliminary results for this, let's say, three type of scenarios. So a baseline scenario, baseline projection. From a CG perspective, the baseline projection, although it seems straightforward, is not at all, because you have to assume not only the aggregate GDP growth rate, but the components both from the supply and demand side, and then how these components per country match the respective assumptions from the other countries and other sectors, given that they are all linked together. So, for example, you cannot grow a sector if the demand for its products is not available, both from a domestic and international perspective. So you have to match the sectoral, let's say, production, the consumption patterns, the, let's say, population growth, income, gross fixed capital formation, demand, the sustainability requirement, for example, that from an economic perspective, that deficits or surpluses have to be reduced over time, excessive deficits. So the baseline scenario is actually a projection that is a construction from a CG perspective, and actually lays the foundation to do all counterfactual scenarios. Now, in this particular, let's say, scenario, the baseline fits the SSP2 pathway up to 2050 in terms of overall economic activity and population growth. Then a climate scenario has been produced well below 2 degrees, and then three circular option scenarios, and one that includes all was possible to make with a model, and I will explain how we did the close, the slow, and the narrow. So if we can go in the next slide. Yes. So here is now the GEMI 3 implementation of close, slow, and narrow. So in the close scenario is about replacing primary and secondary production. So in buildings, let's say this is the first very important, let's say, change. And this has been done with a shift in the investment matrix. So when, let's say, you construct a building, how much you need from secondary, let's say, resources, secondary material. The same is for transport. So we replace primary with secondary production in producing, in manufacturing vehicles. And this has been changed, let's say, in the production function of, so the choice between the two of the transport manufacturers. So in both cases, the potential to go to the secondary production is also constrained by the availability of recycled material, scrap, of secondary resources. On the slow scenario, we have been able to model through the extension of lifetime. So actually, essentially, to keep in the economy equipment for a much higher period, longer period. And the narrow is about material substitution. So, for example, in the production function, the substitution between cement by wood, less passenger kilometers in transport, and high material productivity. Now, before going to the next slide, I want to remind you this CG aspect that, for example, if you make a modal shift and you don't drive your car and you go take the bus, this has a positive effect on emissions and energy because for the, let's say the same passenger kilometers are delivered with different means. Or if you drive less, this again, of course, has an economic impact, an energy and emission impact. But from a CG perspective, you save money, so you don't do this or you don't do which are spent, which means that there is this rebound effect in the results of the model where actually if you have or you create something that increases economic activity, then you are going to increase energy, you are going to increase emissions by consuming or producing something else, something different, because the system is closed from an accounting perspective. So if you save, let's say income by spending less, then this income is spending by spending less, for example, in transport, is spent in other purposes, which drives, let's say, the economic activity. So if we can go to the next slide. So I will not stay here much. It is about the baseline scenario. I mean, China grows in a very high growth rate. I think also India is becoming one of the, here is not shown, of the biggest countries in the world. Population declines or stabilize gradually, and EU mostly grows on a balanced path with investment and consumption, but most is on consumption. So if you can go to the next slide, please. Now, I will go very quickly here on the parameters that we have used in order to, let's say, represent the circular economy options. So material productivity. In the investment matrix, it is, let's say, shifts between different economic activities. In the production function, changes on primary and secondary options. Consumption matrix, changes in the consumption patterns of households. So modal shift, recycling rates, lifetime extensions, taxes and subsidies, and share between primary and secondary markets. So in the next slide, please. All right, this is very short, just to show you very short term until 2030, how quickly the clean energy technologies market changes. I mean, it almost, let's say, doubles. The costs of the technologies also change. This is so the market itself, it depends both from a value perspective and a price perspective and a volume perspective. So you adapt more material or more technologies, but the prices fall over time. So the value of the market does not increase as you would have expected. In the next slide, please. Now, let's see some preliminary results on the GDP and CO2 emissions. So on the left side, on the top two graphs regard the GDP. This is on the left, the baseline with and without circular economy measures. And on the right, it is the decarbonization scenario with all circular economy measures. So you can see that from a GDP perspective, so when you have the SSP2 narrow, slow, close scenario, you have a positive impact on GDP. And also a positive impact, let's say, in the decarbonization scenario. So these policies actually help to increase GDP. If you, however, decompose, let's say, or not decompose, see the three different scenarios, the narrow, slow, and close, you will see some differences. So let's say in the closed scenario, which is about substituting primary with secondary production. Of course, this is preliminary; it's not yet mature. We need to think. It stresses the demand for, let's say, secondary materials after a level which the model actually needs to increase the price in order to balance. So it is not, let's say, cheaper as now as it stands. I'm not fully, let's say, we need to explore further, but it seems that having not available resources to support the secondary production, if you engage in significant, let's say, substitutions, might increase prices after a level which actually produces this effect. From, let's say, from CO2 emissions, you see, again, as expected, most of the scenarios delivered what has been expected. I mean, the best performing scenario in our case is the narrow scenario. Now, probably either we have not been very, let's say, detailed in simulating the the slow scenario. Here, we are missing the labels below, but it's okay. Never mind, it's okay now. The slow scenario increases emissions in the model because as we have implemented now, and probably we need to re-examine, it keeps in the system technologies that are not efficient. So you prolong the duration of vehicles or of, let's say, equipment, which is either carbon intensive or energy intensive. So probably we have miscomputed this, or it shows something. So it is the more you keep these technologies, then the harder it is to replace them after a point. So this is something that we need to consider. Then on the, let's say, on the decarbonizing the energy system, as we said, from a GDP perspective, is quite, let's say, important. From a CO2 emissions perspective, it is, I mean, you have a benefit. At the same time, we have to compute or have into account that the higher economic activity will generate more emissions, so you have this type of rebound effect. And it seems also in the medium phase, so until 2030, 2035, let's say, an important, let's say, element of this circularity, whereas towards the end, where you fully decarbonize, it's less important. We have also to think about that. So these are the main, let's say, insights we got from this preliminary branch. In the next slide, we are going to show employment, which still requires some thought, but it seems to be quite strong here. In 1.5 minutes, I will be finished. So from employment perspective, it shows that the circular economy options are much better because you increase activity GDP, and at the same time, some of these activities are more labor intensive than, let's say, the previous ones. So if we can go in the next slide, this is the final one. So the challenges here is on one side to, let's say, properly represent the substitution possibilities of primary, secondary, let's say, between primary and secondary production, the availability of scrap, of recycled material. And once you have that, the model, because it has this horizontal, let's say, wages or cost of capital, finds it very beneficial once you find ways to reduce total costs. The lifetime extension is something that is important, but also we need to consider which technologies actually you keep more into your system and whether this makes sense from an emissions perspective. So I will stop here. Thank you very much for your, let's say, attention. Thank you.
Okay, so we're moving to the Q&A part. So we're just going to check online. I think we already had one question.
We had one question from Eli Isa, and I think it was for Peter. because it took place at 9:30. Is the expected lower primary demand in developed countries based on scenario result modeling the future with current policy trajectories? Yes. Also in developed countries.
Can you repeat the question, Asel, please?
Lower demand in developed countries based on scenario results modeling the future with current policy trajectory.
In the baseline, there's already much lower primary material demand for steel in developed countries before circular economy. Then the circular economy strategies increases this further or brings this material demand down further. This is the case for primary for steel, at least.
Yes. So thanks, Peter. Are there other questions from the online participants? And feel free also to just raise your hand and unmute yourself. Yes, please.
Hello, hear me? Oh, sorry.
Go ahead.
Okay, my question is to Leonidas, and the question is about when you implement the slow scenario, it looks like the carbon emission in the stage of manufacturing the products and using the products, there's a kind of a trade-off, right? And your result looks like if we extend the lifetime of the vehicles and then the emission associated with using that is much higher than the emission associated with making that. So I'm thinking if you look at like the renewable energy equipment, maybe it's the other way around. So I'm thinking whether the result is driven by which final products you want to extend the lifetime. Okay, that's my question.
Leonidas?
Yes.
And just to quickly check, if Leonidas speaks with this microphone, can you hear him?
Can you hear me?
Yeah.
All right.
Yes.
Okay, thank you. All right. So yes, actually the short answer is yes. So it depends, of course, on which products you increase the lifetime. In our case, we have increased both equipment but also transport equipment, and it has been a significant amount of vehicles. I mean, a large share of vehicles that have been conventional vehicles and have been retained. So if we didn't have that, for example, so if we said that we increase the lifetime of a machinery that probably is not as energy or carbon intensive, it will be different. Right now, the results are driven by exactly this part.
Okay, thanks. So maybe go to the question that Farsan Amir Gavai asked. Are you there live? Otherwise, you can unmute yourself and ask that question. Farsan? Okay. So you have to, I guess, to go to participant then? Yeah. Farsan, can you try? Asking me. Okay, otherwise, on the reuse and recycling rates of different materials, how they estimated implement into the scenario, does it consider also the available technologies? Maybe Peter, you want to say something?
Yeah. So this is done by in our previous work, we collected what is the current condition and the state of the art for recycling and reuse rates to see in different products and for different materials how it is and how it could maximum be. And it's obviously different per material. Concrete, for example, is more downside aggregates compared to steel, which can be reused in similar form. So the implementation of this is yeah, by comparing the existing rates and then like in the scenarios bringing this up to what we can see is the like maximum optimistic potential. So obviously also if there is a high existing recycling rate, that will bring down the potential of bringing it higher.
And so we made this information on the different technologies available to the modeling groups. Obviously, we don't know exactly yet how well the modeling groups were able to adopt that information. But in principle, yes, it is based on information that's based on literature review. Maybe try to go to the next question from Takuya Hara. It's a question for Jiang. And maybe we can try to see whether we can get Takuya Hara live. If you could potentially try to ask a question yourself now. If you unmute. Otherwise, we will read it out. I would like to know how input coefficients are determined when constructing a future input-output table. And it's a question to Jiang.
Yeah, thank you for the question. And it's tricky for the monetary flows. So we're modeling mostly for the A matrix, the coefficient matrix. So we're not actually using the RAS method to make it balanced, but we're trying to, like for the targeted sectors, for example, the columns and the rows you mentioned, have an improvement on that. And to see the whole changes of the rows or sectors to make sure that too can be balanced. So we're now using the whole RAS because we're thinking the RAS for the whole table can introduce more bias or uncertainty. Yeah, and for a small imbalance can be tolerated. And yeah, we test the result before. Yeah, hopefully address your questions.
Thanks. So let's move to the question of Bennett Weiss. And we can try to have Bennett live. You can unmute yourself if you would like to. And so far, we have little success with the others. So otherwise, we again try to simply read out the question. So thanks for the interesting presentations. Question for Peter. In the Virtus Steel plot, we saw 100 megatons in 2020, which rises 3 to 4-fold in the following decade. What drives the increase?
Yes, I think this might be predominantly about the transition from moving historical data to the modeled projected data, where we do see a big increase in the first decade. I would not interpret that very literally.
So this is apparently something that we really still have to look into in the coming month to check.
I think it's probably that the initial value in 2020 is underestimated a lot. So we see this sometimes in the results that there is a higher value from 1990 to 2010, say, then we have this drop in 2020, then it comes up again. So I think it's just a glitch about going from the historical to future data. Maybe also COVID influenced.
So the 2020 is obviously a COVID year, and the model is sensitive pretty much to COVID in the sense that it has this stock flow dynamics. If the stock, as a result of the drop in GDP, the required stock goes down, then at the same time also the required production goes down by quite a bit, and so it might be that is the main reason. Corian, I think you have your hand raised as well. So feel free to unmute if you can. You have Corian Brink. You have to also maybe get him permission. Corian, can you try? Because I think you had your.
I can, but I think the question is from you because he's using the same invitation.
We can hear you.
Go ahead.
Yeah, I already asked the question. Sorry.
Corian Brink.
But this was the question that you brought in before, so that was already out.
Oh, okay. This is the confusion here. Corian is not completely
Sorry
clear.
for that.
Okay, thank you. Any other questions still from online? If you want, you can raise your hand. Sure. Yeah. Was Bennett already? Oh, okay. Yep. Bennett, can you?
Yeah, can you hear me now?
Yes, we can.
So I had issue with my setup. Could you repeat the answer to my question? Sorry, I had to do a restart.
Yes. So this big increase from 2020 to 2030 is because the 2020 number is probably underestimated a lot. It's related to the fall in production around COVID time and also the transition from the historical data to the future modeled data.
Yeah, and the sensitivity probably of the model to COVID. So we will look into this. But thanks for the question.
Thanks for repeating the answer. Appreciate it.
Okay, great. So are there any questions also from here? I had a question for Leonidas about the secondary material. Can there be secondary material trade? Something that we see in the building results is that the maybe there could be excess secondary steel, for example, in one country, and maybe that can satisfy some demand in other regions. And I'm wondering, in your modeling setup, is there potential for trade of the secondary material?
Well, I have the potential, yes, there is. I have to look now because I haven't. The GTAP trade flows for secondary material, if they exist or not, and how they are developed. I mean, I know they have. To be honest, I have not seen how much of the secondary production goes, so I have not seen with my eye. But the potential it is, I mean, we have. But it's largely also constrained by the availability of scrapping, of recycling. This is the key.
Yeah. Another quick one for you. The increase in GDP with the decarbonization strategies is for me, it's an unexpected result or interesting result. Is it about the rebound that is causing this increase in GDP?
The rebound is because of the increase. So when you have a material productivity, so you will use less steel to make the same building or the same car. From a CG perspective, you release resources, productive resources, to be employed elsewhere that are more productive. So to the extent that you increase productivity, or to the extent that these measures can lower carbon, not the carbon price here, but the taxable. So if you have a fixed carbon price, but you have lower emissions, so this reduces the costs in some cases, production costs, and hence sales and consumption. This actually will allow, as you saw, GDP, as compared to the baseline, drops with the circular, but it's at a higher level than when you don't have the circular economy options. So you have a negative impact on GDP, as you saw the two lines were going downwards, but it's not as much as if you don't have the circular economy. And it is because of this reason. The rebound effect is that you free up production factors to be used elsewhere. You increase economic activity, hence you need more material, more emissions, more energy, and this was actually has this impact.
Thank you. If there are no further questions, then.
Yes. May I ask a question, not being a modeler? But when I look at the slow strategies, I'm wondering if the models take into account that to use something longer, you sometimes need a higher quality, which might have a higher demand for the input. Is that represented?
Well, not, and at least not explicitly. Yeah? So in the model, all these behavioral quality parameters are reflected in elasticities, so in a more abstract or general way.
You might want to say quickly something also on the work that you are doing for the use of materials during use and the potential increase in that if you prolong lifetime.
Yeah, so the research that I've been doing on the maintenance of vehicles has actually shown that this material demand is higher than I would have expected. It's around 30% additional to the material demand for production. Yeah, that's quite an interesting insight. So this is actually quite relevant for a circular economy discussion, because for lifetime extension, this means that lifetime extension is not free from a material perspective. And this is something that most material models actually don't consider. So this is quite interesting.
Okay.
Yeah, no, because this is a very good point. There is also the issue that we sometimes mix together data sources that report the technical lifetime, which might be much longer than the actual used lifetime of certain products. So technically, they are already made to last longer for specific things, while in other cases, it's the opposite thing.
Francesco?
Yes, we're not taking care directly about we're working with another CG model. We are not taking care directly about the quality, but we impose that you need more maintenance work if you have more, you use for longer time the everything. So you need more spare parts, you may need more repairing. So we are taking this into account in the simulation.
So okay, quickly then.
Yeah, a quick response to the lifetime thing. For machinery, we also find one thing interesting, also relevant to the Peter's one. Just like because machinery are often, when obsoleted in the developed countries, probably will ship to the developing countries to maintain another kind of services. So it's hard to model or hard to capture there. Yeah, the other kind of thing, just like for lifetime changes, especially for the textile, the fashion industry, we have some studies alongside for that. For example, the lifetime of the clothes are changing quickly in the recent years, but there's really a large data gaps of that. Yeah. Also, a very quick response to the secondary construction waste. We have a study on that. Probably also depends on the transport radius. Construction waste like 50 to 100 kilometers. So yeah, we hope that can happen, but it's constrained by the distance. Yeah.
Thanks. Yeah, we have to round up because we're already a little bit over time, and it's actually nice that the discussion became so lively. I think I started this round of presentations by saying that we now had some preliminary results from the scenarios, and that the main focus now is to make sure that we develop that further, and we are sure about the results. We make sure that we improve the scenarios. Actually, I saw really some interesting results already being presented, and also from the different tools that we have available within the project. And so in analyzing the CGE, the CE using CGEs did give us information now on potential macroeconomic benefits. And we saw already that possibly a CE strategy could mitigate the economic cost of a climate policy, which I think is a very interesting result if we can conclude from the project that is a good indication. And also the other aspect in that analysis, I think, we should build upon the fact that you were analyzing the lifetime extension, and that there is potentially also a cost in terms of slowing down the technology transition, and therefore potentially leading to more energy use while saving material use. I think that would be an interesting thing to analyze further. Yeah, we also saw in the presentation of Peter how IAMs combined with material flow modeling can help us to understand the potential impact. And we already saw that potentially we could save up to 60% or so of material use in the building sector, which would be an extensive contribution. And also the dynamics across the different regions was something very interesting, I think, from that presentation. Looking into the machinery part, I think is completely unique. It's something that was not done before CIRCOMOD, and I think that is also a really important contribution. So I think already now moving into the scenarios, we see very interesting results. So let's make sure that we use the last months to make sure that we improve on that further. So thanks, and with this I would like to end the webinar. Thanks also from our online participants.
Thank you very much. This way we are closing the webinar.